Hello and welcome to T Academy. In today's lecture, we'll be simulating a half-wave rectifier together with a transformer. We want an output DC voltage of 3.6 volts across the load, which we can model as a resistor. So this is 3.6 volts DC. Let's call this RL. And then we have here a mains voltage of 230 volts RMS, and we'll be using a half-wave rectifier. This half-wave rectifier will look like a diode and a capacitor. So the first thing we need to find out is the peak voltage which appears at the input of the half-wave rectifier, and this we can easily find out because this peak voltage will be nothing but the forward drop of the diode plus the output voltage. This would be 3.6 plus the forward drop is in the range of 0.7 to 1 volts, so we will take it as 0.9, and this will give me the peak voltage at the input as 4.5 volts peak. Now in between the input mains and the half-wave rectifier, I need a transformer block which converts the input AC voltage to a peak voltage of 4.5 volts. So this is 4.5. So let's convert the input voltage as well from RMS to peak, which can be done by multiplying with square root 2. So this equals 325 volts. So we need a transformer which converts 325 volts peak to a secondary voltage of 4.5 volts peak. So the way we model transformers in LTSpice is by using inductors which are mutually coupled. So this will be an inductor L1, this will be inductor L2. So by writing the statement K L1 L2 1, I'm describing that these two inductors have a mutual coupling coefficient of 1, which means that all of the flux that is developed by L1 will be linked to the inductor L2. And this dot convention is extremely important because this tells us about the polarity of the voltage. So if the input voltage is positive and negative like this, then we have to put the dot at the start of the winding so as to have a positive voltage at the secondary side inductance as well. Now we know that the ratio of the secondary voltage and the primary voltage in a transformer is simply the ratio of the number of turns. But in LTSpice, we model transformers using inductances and not using the number of turns. So that's why we need to express this in terms of the primary and secondary inductance. Since we know that the inductance is proportional to the square of the number of turns, we can write the ratio of the inductances like the square of the ratio of the number of turns. And the ratio of the number of turns we know is simply equal to the ratio of the primary and secondary voltage. So putting in the values, the ratio of inductances that we need is 325 volts peak divided by 4.5 square. So this equals to 5216. So if I choose the secondary inductance L2 as 1 millihenry, then the primary inductance I need is equal to 5216 millihenry in order to step down the input voltage from 325 volts peak to a secondary voltage of 4.5 volts peak. So let's go to LTSpice and simulate this circuit. So let's start with our simulation. I'll start with the voltage source by pressing V, place it somewhere here, right click, go to advanced, I'll select sine, and I'll specify the amplitude as 325 volts, which is the peak value. Frequency is 50 Hz, and I don't need to specify anything else. Press S and move it somewhere here. I'll press L1 for the primary inductance, then press again for the secondary inductance, and by using the spice directive I will specify a mutual coupling between the two, K L1 L2 1, and place it here. So now you can see that the polarity convention is not right. We want the positive side of the inductance to face the positive of the input voltage. So I'll select it, press Ctrl R, then Ctrl E to mirror and place it like this. Same thing on the secondary side, Ctrl R, and place it like. Next I'll place a diode with its anode facing the secondary side. Then we have the load resistance and the capacitance at the output. We also need a very small resistance R between the input and the primary inductance. Otherwise LTSpice gives an error that the primary winding is just placed in parallel across the input. So we need to place a very small resistance here. Let's connect everything on the secondary side as well. Let's enter the value of this resistance as 0.001. Let's put in the values of the primary and secondary inductances which we calculated. The primary inductance we calculated as 5126 milli with the lowercase m, and 1 milli on the secondary side. I'll use an output resistance of 1 ohm, and I'll be stepping the value of this capacitance C, since this decides the ripple that we allow on the output DC voltage. So this I can specify by writing a spice directive dot, connect it with wires, and that's it. We have made our circuit. So let's go and simulate it. Press the run button, and I'll simulate it for 2 periods of the input voltage, which will be 40 milli. So first I would like to see the input voltage across the primary inductance, and this, as you can see, it is nicely equal to a peak voltage of 325 volts. Then I'll open a pane below it by pressing B, and I'll take my voltage probe to the secondary side inductance. And this, as we did in our analysis, let's place a cursor here, and if I move it, you can see that this peak voltage is very close to 4.5 volts, which we used for our analysis. Next, I want to see the rectified voltage. I'll open another pane and take my voltage probe to the output side. Let's make it bigger, and from this plot you can see that the capacitor charges, it goes to the peak input voltage, and then it starts to discharge through the output resistance with a certain ripple, and this ripple is decided by the value of the capacitance. So let's zoom in a bit here, and I'll add cursor here on the active trace, and I can move my cursor, I can step this parameter by using upper or the lower arrows. So if I press upper here and then right click, then you can see that the capacitance value for this red curve is 100 milli. If I press the arrow key and then right click again, then you can see that the capacitance here is 150 milli. And the ripple amplitude decreases as I increase the value of the capacitance. So here the capacitance is 350 milli, and you can see that the ripple amplitude is pretty small. Let's zoom in a bit more, and you can see that this brown curve has a much smaller ripple compared to the red and the blue curve. Now we'll do detailed calculations on how we can calculate the value of the capacitance given a certain peak-to-peak percentage ripple, and we'll then simulate it again in LTSpice. So that's it for today's lecture. If you like my videos, then do subscribe to the channel, and I'll see you again in another lecture. Bye.